All right, let's go ahead and get started now that my technical difficulties appear to have been averted. All right, so my name is Mark Sims. I'm a group program manager on the Azure engineering team, primarily focused around building big, nasty applications. You might ask, why is an Azure guy hanging out at a SQL conference? Well, I love you folks, and I actually do a lot of stuff with high-end data repositories, backing services. And what I wanted to borrow an hour of your lives today, which you will unfortunately never get back, is to talk a little bit about the journey of how do you build operational data stores, telemetry, and insight into large-scale services and applications with an eye towards SQL. But this isn't actually a presentation about how to build one. This is a presentation about the journey, the steps, and the choices, and how you go about finding out what works and what doesn't. This is actually a project I'm working on right now, so you guys get to have a little glimpse, a little bit of insight into all the bad things that happen along the way, how we measure, how we evaluate, how we figure out what works and what doesn't. And at the end, you will have more questions than answers. If this does not sound like a great way to spend an hour, there are lots of other great things going on. So, we want to talk a little bit about why is telemetry important in large-scale, highly distributed systems. Whether they're running in the cloud or in your own data center, the problems are actually largely the same. We'll think about an end-to-end view of an application and dive straight into how do we set up SQL Server to accept high-speed logging and telemetry without tipping over. We'll walk through 4 or 5 different options. We'll explore memory-optimized tables. We'll look at natively compiled stored procedures. We'll look at batching via table-valued parameters. But most importantly, we'll look at how do we make changes along the way? How do we measure? How do we evaluate? And how do we find out if any of this stuff actually even works? There's going to be some C#, some .NET, some logging code, a bunch of R for the statistically minded amongst you, and a whole bunch of SQL. If any of these things fill you with terror, there is a lovely door at the back of the room. And since no one has run out screaming, put your seatbelts on, hang on, enjoy the ride. A couple of key things to keep in mind. This is intended to be interactive. If you do not ask me questions, I will ask you questions. My questions will be worse, I guarantee it. All right, and on that note, let's dive on in. So for a lot of traditional 3-tier applications, you've got a bunch of stateless compute surrounding one scale-up SQL Server. And that's a great pattern. It's worked very well for a long time. And if you want to know what's going wrong, by and large, you can go and ask that single central SQL box, or Oracle if you're silly enough to use that. Had to get one dig in. But as we move towards these highly distributed applications in a mobile-first, cloud-first world, it's not so simple anymore. You may not even own or control large numbers of the services. I was working with one customer. It's a big retail shop. Nothing to do with the cloud, but they're so big, the applications kind of look the same. They have 4 segments of their website for selling, let's call it shoes, to pick a random example. And their division, the gentleman I was working with, only sees one slice of it. So when big shopping events happen, they actually have absolutely no idea why or how their site tips over, because there's 4 completely independent silos of telemetry data that don't share information with each other. Not running in the cloud, but still they have 0 operational insight. A lot of moving parts, dynamic load and scale, and there's no single source of truth. If you just log on individual boxes, how do you find out where the problem is? If I've got a few hundred servers, which one is the misbehaving one? And the answer is usually not any individual server that's misbehaving, it's the communication between them. So this is just a simple cloud application just to talk about. Even for a simple app, there's a lot of different moving parts. All right, so has anyone played Frogger? This is an age check. So this is a game from back in the 80s where your job is to take a small, poorly rendered 16-color frog and get them from across the highway, across the river, to the other side without getting run down or drowned. And you may ask, why do you have a picture of Frogger on the screen? And every time I'm working with folks who are running a live site, running a large-scale service, this comes to mind, because for most of them, this is not the game they're playing. This is the game they're playing, which is, there are bad things happening all around me, but I don't know. So this makes me feel better, because I have no idea if my site's about to get run over with a bus or not. So really, when we think about telemetry, we think about insight, it's really just kind of exposing there are bad things happening or potentially happening all around your service. But if we don't know about them, we can't have an appreciation for the risk, and we can't make good choices. So there's two roads, and both of these are from real conversations. Unfortunately, the first conversation is the more common one that I've run into. So I turned off logging in production because it took too much load on the servers and generated too many error messages. Has anyone ever heard this statement uttered? More people will have heard it than will admit it. For a very long time, it's been very common that we do a lot of logging in test. We have our test beds, our QA, lots of logging turned on, we get all kinds of stuff, which is awesome, except for what that's actually saying is I only care about being able to diagnose issues in test. I don't care about being able to diagnose issues in production. It's kind of funny when you think about it that way. But there is a very valid case here, which is if I turn on logging, everything slows down and I can't meet my SLAs anymore. Some folks go down this road. It's the easier one. You just turn things off. You close your eyes and you just kind of hope for the best. But we're here to kind of think a little past that and get down the second road of how do we make the appropriate investments so that I can turn on very rich logging, very rich insight in production and still meet my SLAs and meet my goals. Sound reasonable? So if anybody on the first one, it's easy. You can just stop, we get up now, and we move on. But for the right one, let's dig in a little bit and talk about what you actually need to be able to do to have insight into systems in production. And the metric I use, if you have any difference in operational telemetry between your test environment and your production environment, you're probably going to fail at some point because there's interesting things happening that will only be triggered by real users and real load. Essentially your test load, your test harnesses, will never do the quirky, weird things because if you knew about them, they wouldn't be quirky and weird anymore. They'd just be part of your test plan. All right, so three key things that we're going to work through in terms of this design. We need to instrument for production logging. Essentially, everything we do when we think about instrumentation has to be under conditions of extreme success. Strange phrase. Why is success scary? Because success exposes all the things you didn't think of. When you're wildly popular, way more successful than you'd originally designed for, and 10 times as many people or 10 times as much load shows up in your system, all the little things that you didn't think of, all of the little breakpoints, the brittleness, they just pop out, and sometimes very bad things happen. And if you haven't instrumented for production load, you'll never find them, and you'll never be able to do root cause analysis. Inter-service monitoring alerting. What happens when I go between tiers? What happens when I go between pieces of my service? Do I know that when I called out to Twitter or Facebook or Google authentication, did it work? I can't reach out to those services and get their logs. The only way I get insight is if I understand every time I reach out to a remote service, I have some understanding of what did I call out to, how long did it take, and did it work? And as well as the ability to basically configure this stuff at runtime so I can tweak my operational profile. Okay, so we need to consider a few key things. We need rich logging information. That's kind of a given. But it also has to work in a distributed environment, which means that every log statement has to understand where it came from. Just a server name is not actually all that useful when I have hundreds of them. It needs to have a little bit more context around what was this thing doing? What was its role in the application? Is anyone working on like an IoT device-centric application or maybe in the future? Okay, even if you don't, you probably will. One of the things is if you have a message-driven applications, a mobile device connects into an app and tries to do something. A device sends a message, tries to do something. Unless you can trace the path of that request all the way through the system, from a web tier to a worker tier to a database to a third-party service, it's really hard to figure out what went wrong or what went right, especially if someone calls up and says, hey, my thing didn't work. Well, okay, a million things happened in this hour. Which one was yours? So unless we can correlate individual workflows and individual activities across tiers, we're kind of running blind. This was probably one of our biggest learnings in building Azure, is that without the ability to basically get very granular telemetry and trace every step through the system, production diagnostics was nearly impossible. Granular filtering has to be full production logging, but most importantly, logging has to be fire and forget. Ironically enough, a lot of the folks I've worked with who have gone down the road of trying to do production scale logging have actually tipped their services over because of the impact of logging. Let's look at an example. This is This is actually from a real production service for a bunch of connected devices that had an SLA that says, I cannot have any call take longer than 2,000 milliseconds. If anything takes longer than that, it's out of SLA. And if we peek here at the bottom, just in this call stack, the piece at the very bottom took 2,200 milliseconds. So essentially what that was is, if you're familiar with the Win32 API, it's basically the cost of acquiring the tail pointer on the logging file took longer than the entire operation was supposed to. So this is not even logging to a remote resource. This is actually just logging to a local file. But because under conditions of success, there were so many log entries being emitted, there was basic contention on the file. Happened to be, this was log4net, which has well-known issues for contention under high degrees of load. But this will never show up unless you're deliberately doing breaking strain testing. Unless you hammer your test environment with so much load that it actually tips over, you won't find these things. So this is just a very straightforward example of a perfectly functional system that had been running for months that suddenly got very popular on one certain day and tipped over because the log configuration was incorrect. I actually see this quite a bit. And if you think that a local resource like a file is relatively low latency, you can do a lot with it, imagine what happens when we want to reach out across the network to, say, a database and start hammering logs in. What are all the bad things that can happen? So we'll go through those. All right, so we're just going to go through and think about, don't focus too much on NLog itself. It's just a logging library. If your devs are doing logging, you should probably tell them to use this or something like this, because it has a couple of nice features. We can plug in various targets, like SQL, it comes with one out of the box, and it allows to do asynchronous operations, so that fire and forget experience. If you have synchronous logging in your apps, or your devs have synchronous logging in their apps, what will happen is any latency in the underlying logging framework will directly transmit to the user experience, and that's a very bad thing. You don't want users' experiences impacted because of an inherently lossy logging experience, because it's logging. If we have to throw away data in order to preserve user experience, we'll do that. If we can't throw it away, it's not logging anymore, it's auditing, and that's a very different kettle of fish. All right, so let's walk through the experience of setting up NLog against SQL to survive success. Sound good? Only one person ran out and he wasn't screaming, so I think we're doing okay. All right, so let's just do, and I'm going to get out of PowerPoint and actually get to some code very soon here. Let's just do some very basic stuff. Let's do what all of the logging documentation and best practices would have you believe, that let's just insert stuff into a table. So we're going to come over here to my, my little dev VM in Azure. Fantastic. And we're going to go to our, that's great. There we go. We're just going to go to a basic log table. So again, nothing really special here. Just your bog standard table. There's a couple of fields for a host, role, and instance, a level, logger, message, exception. And you go on like any of the log documentation samples, this is the kind of thing you'll see. Create a basic stored procedure, drop stuff in. Pretty reasonable, so far, so good. Very straightforward, very simple, very dangerous. So let's actually just go and run a few tests. So I bought a little copy of Atom Mechanics' handy little SQL query stress tool, and I'll just come in and just run some basic tests. So I created a little USP test log. I created a little stored procedure called test log, which basically just lets me go and I did create one, didn't I? Okay, apparently I've created a lot of metadata there. Yeah, there we go. Just a little stored procedure called test log, which calls insert log for me, so I didn't have to futz around on the client side with setting up a bunch of stuff. So let's just start off. We'll just do one iteration in one thread. Okay, and it blew up, of course, because there is insufficient system memory and resource pool. Apparently, SQL decided to jump ahead to the next part of the demo, which is where I break it. And there's a test running in the background, which has actually apparently shattered the database. So we'll just pretend that I didn't do the demo out of order. And I'll actually go turn off that test and reset SQL and then go back to my carefully chosen slides, just for eventualities like that. So probably in about 10 minutes, I'm going to ask the question, where does this all break? Strangely enough, you guys actually already know the answer because I already broke it. Okay, so let me just reset this, and then we'll go back to some slides. Okay. Now, really, I want you to restart. Thank you. Okay. So through the magic of PowerPoint, we go run this query tool. It does a nice job. Can basically run concurrent iterations and concurrent threads. Because this is a logging experience and we want it to run from a bunch of different machines, we're going to expect concurrency by default. And the interesting thing is when we go and we actually graph the data coming out. So this is basically the performance from the baseline single row inserts using the SQL query tool and basically looking at concurrency. 1 concurrent thread, 10 concurrent threads, 100 concurrent threads. And even just from this, some really interesting patterns start to jump out of the data. Specifically that we see a really great jump in throughput going from 1 thread to 10 threads. Makes a lot of sense. We actually don't see very much improvement at all going from 10 to 100. So the immediate thought is, hey, there's some form of concurrency bottleneck here. It might be on the client, it might be on the server, but for whatever reason, I can't easily go from 10 to 100 concurrent threads. And this is where the logging framework behavior comes into play. Every common .NET logging framework out there, and pretty much all the Java ones as well, by default will essentially create one call or one target call for every log record. So you go log.trace something, and that comes down to the database logging target, and then fires off a single record insert. So under conditions of extreme success, we're going to start stacking up, and the concurrency is going to get really large really fast. So if we see concurrency issues here with 10 concurrent threads from one box, or 100, imagine when we have 100 VMs running. This could be problematic. So let's dig in on this and see if we can't do some optimization. Okay, so one of the first things might be, well, I wonder if the actual contention on the transaction log could be a problem because it's a heavy insert volume. So maybe I'm just going to go to memory optimized tables. For anybody who was in the previous session, there was a lot of good information about that. So I'll say, okay, this is log data, and I've got SQL 2014 and Hackathon. Sorry, I keep using the internal code names. Is really awesome. So I'll just make a few small changes to my table. I'll set it up for memory optimized being on. I have to lose varchar max because every row has to fit in a SQL page, 8,020 bytes or so. And if I really wanted to make this thing scream and I didn't care about losing data, then I could just go with basically a schema only and just hold the tables in memory. So far, so good. I'd go and run this live, but I imagine I'm still rebooting in the background. So a good performance increase, minimal changes, and but I'm still seeing that interesting concurrency bottleneck between 10 and 100. But okay, that's not a bad change. It wasn't an expensive one. I didn't have to do a lot of stuff. Let's make a few more tweaks. So one of the things that I was doing back here, in the insert was I had a little table that mapped from info, warning, error, debug into some levels. But that wasn't a memory optimized table. So maybe we should go and actually memory optimize all of the tables that are being used here. That might have an impact. Okay. So we go and we set up the levels table to do to be memory optimized as well, specifying the collation. This is just one of the little things you have to watch out for with memory optimized tables. And memory optimized on, durability, schema, and data. And it turns out that's really weird. Part of this is a journey. You don't always get the results that you expect. I would expect that having added, making everything memory optimized, this would get faster. I certainly didn't expect it to get slower. That's really weird. So part is pulling back and going, a couple of interesting questions. Was this observation statistically relevant? I don't know, was it? The hint is I only ran this test once. Was that enough? I don't think it is. What do you guys think? This could just be random. It could have been someone else logged into the server and kicked something off at the same time. So just having n equals 1 doesn't mean I can trust this data. There's an interesting pattern, but I don't know if this is real yet. And the other part is, were the measurements and the visualization accurate? Of course, since I put the question up there, you know the answer is already no. That this was not good observation, this was not good data. But it was at least a starting point. And I'll dig in a little bit later as to why this was not a good measurement. But the hint and kind of part of the theme we'll carry through is that averages will tell you lies in performance optimization. They will tell you very nasty, dirty lies. And we'll show what some of those lies look like in a second. Okay, so sometimes the issue isn't what you're measuring, it's in how you're measuring it. There have been so many times I've been bitten by having this great hypothesis, charging off, making all kinds of changes, then realizing a day or two later, like, yeah, the data that I made that choice, it was bad data, or my interpretation of it was wrong. So it's always good to get a second set of eyeballs and validate your measurements. Don't get fixated on the low order bits. We've talked a lot about optimizing single row inserts here. We've gone through that journey. We've done a little bit of in-memory optimization. We've kind of tweaked a few odds and ends. But at the end of the day, I'm never going to be able to create a high-speed logging experience or meet my business goals by logging one record at a time. I'm just fighting against physics. So I can do all kinds of optimization on that single row insert, and it will not help me at the end of the day because that's the low order bit. I've got to change the question, I've got to change the approach to focus on what are the truly transformational things that I can hit. And again, in performance optimization, we call these micro optimizations, and they're very easy to rat hole in. Look, if I just spend another 2 or 3 days, I can get another 1% out of this thing, as opposed to, maybe if I go over here and I look at the system end to end, for half the amount of work, I can 10x something. So again, it's the don't get fixated, pull back, look at the end to end and go, are we really focusing on something? Is there more goodness to get out of here, or do we need to kind of go upstream or look at a different piece of the system? Performance, it's an exploration. Not every avenue yields results. And the things that look really promising, but you end up rat holing on, can be both horrible, and they can also cause regressions. Any number of times I've been like, hey, maybe we'll go fix this thing. And it turns out I actually made the system worse. So the other part of that is always be able to undo. I don't know if we basically source control, snapshots of databases, just always be able to undo any change you make. But ultimately, understand the metrics that matter to your customers and to the business value you're trying to deliver, and how that performance data can be skewed. So ultimately, in terms of we're looking at building logging. In this context, the only performance metric that's really relevant is, does logging affect the end user experience? Honestly, as soon as we go asynchronous, we've actually taken all of that latency and that time impact out of our end users. They don't see it anymore. Then it just comes back to how are we optimizing for our own operations team. So all of the work we do on the back end, as long as it's not directly tied to the front end user experience, we have a lot more wiggle room. But it doesn't, if logging is synchronous, it doesn't matter how good a job we do on the database, it's always going to have a negative impact. So just how and where we make these changes, and sometimes you have to push upstream.
Can I, as a DBA, understand how the logging is done, if it's asynchronous or synchronous? If I don't know how they are repeating code.
So the question is, from a DBA perspective, can I tell if my developers have made good or bad choices? If I can translate a little bit. The answer is unfortunately no. From a DBA perspective, you actually will not see whether or not logging is synchronous or asynchronous. But what you can see is if it's constrained or unconstrained in concurrency. So if you see, and we'll show this in a little bit, if you see like a metronome, a very periodic, every second I get a batch of log data, that's great because it means the upstream system is bounding concurrency and it's handling batching and aggregation correctly. If you see these huge spikes of single row inserts, someone upstream is doing very bad things and not treating the database with the respect it deserves. We don't like that. So you can see some things, you can't see some other ones. All right. Strangely enough, the reason that that chart looked weird was I graphed it wrong. Stupidly simple, but when I clicked on the Create Chart button in Excel, it automatically pulled in the wrong fields by default, and this is what that chart actually looks like when it's plotted correctly. Sometimes it's the simple things that trip you up. Actually, as I was building this deck, I realized I'd made a mistake when I put the graph in, and I decided, no, this is what happens every day. Let's leave the mistake in and then come back. Because part of what I did was, I don't believe this graph. I don't believe this data. And I went back and actually validated and went, oh, I'm actually pulling from a different set of rows. So now that we've actually gone and tweaked the data, it looks like, there doesn't seem to be any real statistically relevant difference between going with the log data being memory optimized and everything being memory optimized, which makes sense. If I have a table with 4 rows in it that I just do queries and joins on, I'm pretty sure that's always going to be resident in memory anyway. So forcing it doesn't really help me all that much. But ultimately, we can keep going down this road. We're never going to get ahead of the game. We're never going to get to thousands and tens of thousands of records a second. We've got to change this up a little bit. So let's go batch inserts. 2 options. I can bulk insert, or I can basically use table valued parameters to batch data in. Bulk insert works really great when I have a bounded source set. So in an ETL pipeline, I have a bounded set of data to pass in, even if it's a set of files that are showing up. So I crank open a bulk insert context, I hammer data, and I close it down. The problem is there's a certain amount of time and cost involved in establishing that bulk insert session. And the number's a little loose, but it turns out that 128 rows is actually about the magic number. If you have less than 128 rows of data, table valued inserts tends to be a little faster. And if what we're looking at doing is creating a diagnostics experience, especially in a dev test scenario, I don't necessarily want to wait long enough to buffer up enough log data to make bulk insert worth it. So instead, I might want to optimize for latency and interactivity for my ops personnel and just shovel stuff in with TVPs. Neither one of these choices are wrong. I'm just optimizing for different things. In fact, we might go a little further down the road and go, you know what? In production, we're actually logging so much, I can always keep a bulk insert channel live. I don't know yet. This is why it's a journey. All right, so for handing in a table valued parameter, I just need to define a table type. And the only trick is I just define the table type as memory optimized, and it still has to fit within a single page. So I can't have message and exception data. I just have to have my log data. All right. Again, the assumption here is as soon as I expose this, I have to have a way for my developers upstream to buffer and batch data. Good news is NLog has a buffering wrapper built in that you can basically say, hey, your responsibility is just to accumulate in a time-space buffer, at least up to 128 records, send data at least every 5 seconds, and then we set the stage so we get good data down. We get the ability to do good things when we reach out to SQL. Okay. So again, the code is really simple. The only little tricks are I just basically want to have an atomic transaction, setting up transaction isolation level of snapshot. Because again, I'm not worried about tight consistency here. It's just log data. If I have to wait an extra, 500 milliseconds, it's okay. It's not a big deal. And just a simple insert, select from, and off we go. All right. So, what does that look like? So here's the interesting thing. Now that I've gone to table valued parameters, that lovely little SQL stress tool I saw earlier, it's not going to work anymore because all of a sudden I've got a TVP. I need to be able to create sets of data, and I need to be able to execute them continuously. And I was looking around, and I couldn't find an out-of-the-box query tool that would let me do this and get good data. So I needed to build a load harness. But here's the other thing. What was wrong in terms of getting a high-fidelity, reasonable representation of the impact on my database from calling that SQL query tool? Where was I calling that tool from? sorry, I was calling, yeah, you're right. I was calling it from localhost. There was no network transition here. I wasn't paying the cost of going out across the network. And because the system I'm actually trying to figure out if it works or not is dozens or hundreds of servers posting across the network to my log database. So if I'm testing from localhost, I don't have a high fidelity test because I'm not taking network latency into account. And if I'm worried about concurrency, then the effect of network latency may create spikes or troughs in my overall load. So in order to get good test data, I need a better test harness. I need something that looks more like the real system, but still allows me to control more of the variables. So it turns out, in retrospect, all of the tests we did with the SQL query tool, they're good for understanding the effects of schema changes and individual items. But it's actually not very good data for finding out if the end-to-end system will work because it took a critical resource out of the system. We see this a lot. So I got a call a couple weeks ago from someone who was working on a website for a very popular American sports athlete. And they'd set it up, and they'd done all their load testing. They said, hey, everything works great. Let's turn it on. This gentleman announces the site, and then 30,000 requests per second started happening in about a minute. And the site immediately melted down. Like, I think it actually caused a hole in our data center where the server caught fire and just puddled into the floor. And I'm on an airplane at the time, watching my Facebook feed, and I see this gentleman post a note saying, hey, you guys are smart, you broke my site. And I'm thinking, hey, it'd be fun to help him fix that. Then my phone rings on the airplane. And of course it was, hey, we're having an issue with this site, can you help out? It turns out there was nothing inherently wrong with the code. What had happened was, if you think about this kind of application, there's a couple of different resources. There's the ones we think about, web server, calls, database, data, all that good stuff, which is great. And all that stuff worked fine. The problem is the way that it had been built from the mobile application side. The mobile apps opened a connection, held the socket open, and then used kind of low latency communication. The challenge is the tests had been done from standard stateless load testing tools that emulated browsers. They didn't emulate mobile applications. So what happened is the front end ran out of sockets and tipped over. The test did not accurately reflect the production environment or the production load. So these folks had what we call a production learning moment, which is a really nice way of saying your boss is calling and is very, very unhappy. Turns out, we deployed additional front-end load balancer capacity. Everything worked fine. But kind of the moral of the story is, when we're doing testing, it's got to look like real load. Otherwise, we build a false sense of confidence. And it's got to pay attention to all of the appropriate metered resources. In the case of the log inserts, this local query stress tool takes into account the local resources, CPU, memory, network, threads, transaction log impact, all that good stuff. But it doesn't take into account what happens when I need to create n number of connections from all these machines, as well as the network latency and the network transition time. This local host, this is cheating. Because when you, on the Windows TCP networking stack, when you establish essentially a local host connection, it bypasses the network card. Basically goes, oh, you wanted localhost. Let me just create an in-memory pipe and just route you directly. It's significantly cheaper. It doesn't load the network card. It just has a very different load profile. So this was telling us lies. But okay, so let's come back here. So the other things that we needed to do was we need to write a simple little .NET app because we're assuming that we're logging from .NET, so that would be a reasonable fidelity. But the most important thing is we would like the timing API to measure the latency of success of every single individual call, because I don't feel good about the averages. I'm thinking something interesting might be happening with regards to the outliers. So really what we want to do is do a parametric sweep, which is just a fancy way of saying I want to run 1 thread, 5 threads, 10 threads, 100 threads. I want to run 1 log per batch, 5 logs per batch, 10 logs per batch. I want to sweep through these parameters, and I want to look at the data and then find where's the sweet spot. I know that 1 thread and 1 log at a time is probably not very good, And I know that 10,000 threads and 10,000 logs at a time is probably going to blow something up. Actually, it's no probably. You already saw the broken thing. So let's dig in a little bit and actually look at how we might do these things. The approach here is the key thing, because this works whether we're looking at optimizing log data or any form of these distributed activities. This process I use pretty much consistently for all the end-to-end performance engineering. So really very simple bit of code here. So when I want to use a table of valued parameter in .NET, I usually construct a data table or another type of schematized array. I say there's a parameter. Here's the name of the TVP, here's the type name of the TVP, and then just execute the query. And then at the end, I just want to use a little stopwatch to say how long did this take. And I've got a logging API that says, given a context and a time and an identifier, just generate a set of data. So what this data looks like is essentially just a log record that says the time, the machine that it ran on, the stored procedure or the method that I was calling, how long did it take, what was the activity identifier. In a production site, if a customer calls up and says, hey, here's the activity ID that was associated with the stuff that failed, and if I actually have activity IDs splintered or spread throughout my tracing, I can actually say, oh, hey, you made, in order to basically buy this thing, you needed to make 15 database calls, and this was the one that was slow. And it turns out it actually wasn't an issue on the server, it was actually an issue in contention on the client. We can start to explore and find these things. All right, so let's actually get out of PowerPoint and let's actually crunch some data. Okay, I'll zoom in on this a little bit just to make it a little easier to see. So I have that, so from a bunch of runs, I have that raw data. It's really simple. Just context, elapsed time, identifier, and a nice little code that basically just says 10 threads, logs per call, 1, and an iteration. So what I'm going to do is just run a little log parser script. Anyone use log parser? So, a couple hands. If you have to basically crunch log data, this is a really nice way of doing it. Especially if you need to go ad hoc. In a more structured form, when you already know the shape of the data and you've operationalized it, basically BCPing this data into SQL is great, but when you just want to explore and go ad hoc, this is a really efficient, very interactive way of doing it. And you get a very SQL-like language. So this is basically just, I'm just going to select out a bunch of stuff. Actually, let me just go have a look at the raw data for just a second here. So let's just look at the top 10 logs. Happen to know it's CSV, so we get our API, our elapsed time, event ID, and the messages. So I need to basically take this elapsed time and turn it back into some form of milliseconds. Good thing is log parser has reasonably good text parsing capabilities. So you'll just see some of this to real, extract tokens, multiply by 60,000. This is just take the .NET time span field and turn it back into essentially just a real number that I can execute some calls against. So I just go and I get my group by API, my thread count, my logs per batch, and my error codes. And actually let's go and look at a successful one before we get to the ones that are broken. So I'm just going to go and add some files from a run that I did earlier. We're just going to add those guys in here. And I'm just going to crunch that. It's a fair bit of data. So let's look at what we got here. So I see if I had one thread and one log per batch, I called that 1,433 times. The average took 11 milliseconds. The minimum took 7 milliseconds. And what do you mean the maximum time took 467 milliseconds? Wow, that's a pretty significant drift there. This is a little easier to see graphically, so we'll just bop back to the PowerPoint for just a second. So one of the things I did was, again, starting from that raw data. I just had to reboot my machine because of some fun with visualization. So let's just go and have a look at my good friend Excel. So we can see that this is the data, basically just plumbed out into Excel. This was my average, min, max, all set up there. So then I just did something where I said, all right, let's just go and basically create a throughput adjustment, which is for the number of messages in the row, or the log records in each call, let's just basically create a normalized view of how fast messages could be published. So smaller numbers are better. Now if I come out and I have a look at the, essentially the data, I hope I'm not, we're going to end up, there we go. I was hoping it wouldn't be basically me up here waving, talking about data. It's very embarrassing. So let's have a look at the data. Behave. We're going to find out if that worked now. So who's ever been presenting and had this happen to them? You know you're out there. Okay, so while we're praying to the demo gods that the visualization comes back online again, I'll just talk to it briefly. Wow, that was cool. Well, I got through most of it before this happened. So it turns out that the tipping point is about 10 threads and 100 log records per. That actually gave the best performance by a factor of about, it's a factor of about 10 or 20. It turns out that one thread, obviously, not very efficient. 10 threads, good. 100 threads, slower than 10. That makes sense. So there's contention on a resource. So what's the default connection pool size for ADO.NET? It's 100. So by default, if your devs are just creating a SQL connection and opening it up, there's 100 pooled connections available. So likely what's happening at 100, because I didn't turn off connection pooling, which I should in this world, because I want to hold on to that connection because I'm going to be continuously hammering it with log data. At 100, if there's 100 items in the pool, I give back to the pool and then I pull from the pool. So I'm probably thrashing my connection pool at 100 concurrent threads. Or I'm hitting some contention on the back-end server. Because all of this testing just took into account one server, I'm not sure where the problem is. I don't know if it's me, if I have a local resource contention, or if I have a remote resource contention. But it's easy to find out. Run this test on 4 or 5 boxes as opposed to just one. But again, add one element at a time. Start from one box, validate, understand, add 2 boxes, add 3 boxes, add 4 boxes. All right. This would look much better, of course, if that wasn't blank. But since we're all here anyway, I'll just... Okay, I got all excited there for a second. So the other thing I was going to do was actually do the statistical breakdown of the data. Because min, max, and average is interesting, but it doesn't really tell me, are those outliers actually relevant? Do they happen enough to matter? So you can't see it, but let's just all pretend along. So has anyone used R before? A couple hands. So I'm very recent, kind of learning R from after barely managing to scrape through statistics in university. But it's very accessible, and even if you just kind of get used to a few recipes, you can do some really interesting analysis in R. Specifically, one of the things that I did, and I'll post this deck later in case folks want to go back and have a look, is, all right, take the full data set, pull it into R, slice out the 10 threads, 100 logs per thread that I like, and just run 3 things. Okay, now I can't even talk. At this point, I'm not even able to see you guys in 10 minutes. Okay, there we go. Sorry, folks. To my EV guys, I really appreciate how hard you guys are cranking on this. I'm not making fun of you. I'm making fun of me. So I basically just use R to create a bar plot. Just basically show me a list of the elapsed times, and you get this nice little, oh, that's neat. You get this neat little basically graph that I can show in a little bit. But the other thing is I want to do a percentile calculation. I want to know that, you guys are awesome. Okay, so now that you can see the data that I've been talking about, so I run this little R query, and then I basically want to generate first a bar plot showing, hey, these outliers, they happen, they might be, actually, that's a really regular pattern I see there. maybe there's actually something that happens every, oh, I don't know, so many seconds that causes it to go offline. Interesting avenue for exploration there. But if I sort them, I see that my long tail is actually not too bad, but the really relevant one is what's the percentile breakdown? It turns out that at 10 concurrent threads and 100 log records per thread, 95% of all calls complete within 193 milliseconds. That's not that bad. That gives me pretty good throughput. But above the 95th percentile, it can get pretty big. So upstream, at the developer side, I need to understand that, hey, this call can occasionally have variation. Now, I don't know what that variation is yet. I don't know if it's transaction log contention. I don't know if it's transactional contention. I need to change my isolation level. I don't know if it's just how I'm marshaling that SQL, kind of the calls. But I know that there's variation. So if the variation matters, I need to go chase it down. If the variation doesn't matter because statistically it doesn't happen enough, I go, it's good enough, and I have an infinite amount of work to go do, so I'll just put it on the backlog, call it a P2 or P3, and keep going. Not every problem actually needs to be solved, but you at least need to know that they're there so you can plan for them. So let me just kind of see if I can't go out and actually pull up my R file, now that you guys can see it. Okay, so basically all I did was just take that raw CSV file, suck it into R, basically just saying read a CSV, and then create a grouped aggregate using this wonderful little ddply function. I have no idea what ddply stands for. Apparently the folks who work on R are fond of very short, meaningless names, but that's okay. I can just cut and paste from the web just as easily as anyone. And all I do is I say I want to group by my thread count, my logs per batch, and then I want a function that basically gives me my mean, min, max, and standard deviation. And that creates something called ags2, very, originally named aggregation2 function. So I'm just going to go and look at ags2. So here we just have a nice little table with our thread counts, our logs per batch, and our mean or min or max and our standard deviation. That's kind of hard to read. That doesn't really visually pop anything out at me. So that's where I take that data and I cut and paste it back into Excel because, well, we're going to use a lot of different tools here. Oh, I think I broke it again. Oh. I did break it again. I should probably not do that. But the screenshot we're looking at earlier kind of broke it down was, okay, statistically speaking, the outliers, the outliers at 10 threads don't really mean all that much. The outliers at 100 threads, very, very bad. All right, let's just go back here so I can get back on topic. So we've been through a bit of a performance evaluation. We've looked at a bunch of different options, and we're left with a set of knowns and a set of unknowns. We know that memory optimized tables together with TVPs for batching appear to provide acceptable performance within the bounds of the test that we've run. We know that there is an upper limit on the performance I can achieve by just working within SQL. I need to take a holistic approach. Some things need to happen at the application level, some things need to happen at the SQL level. I've got to involve my dev teams. They have to help make good joint decisions, otherwise bad things happen. And believe me, they want this log information because they're the ones that are going to be on the hook to actually do diagnostics. The optimal configuration looks to be about 10 threads with 100 items per batch, but I didn't do a full parametric sweep. I went 1, 10, 100. The sweet spot's probably somewhere in the middle there. So it might make sense to go back, and since I've automated this, just run another test. And the 100 client-side threads appears to suffer from contention. And I'm choosing my phrasing very carefully because I have data, I have an observation, I have a hypothesis, and at this point I haven't conclusively proved any of this. I just have a sense from looking at the data, these are the problems that are going on. But my unknowns are actually the most important piece. What happens above 100 threads? You guys know the answer because you saw it at the first 10 minutes. Any guesses? I blow out the SQL VM, I blow out the SQL memory pool, basically. Because I'm basically actually no, it's not actually above 100 threads. Above 100 threads, everything is fine. When you get above 100 log items per batch at above 100 threads, things tip over because the amount of basically memory I need to suck in those TVPs blows out my SQL box. and which in this case actually required me to restart the box. Part of this comes back to the only way to handle this is you can absolutely basically just put a upper size limit, saying that if you call in and the TVP has more than X rows in it, I'm just going to fail it and throw it back. A good little guard there. Better is going back to your devs going, okay, you're not going to send me any more than, say, 100 records, and you're not going to basically send data to me with more than, say, 10 threads at a time. We have contention. Right now, I don't really know if that's client-side or server-side. I would need to dig in more carefully. If it's client-side, it's relatively easy to fix. If it's server-side, that's actually a bigger problem. If I have actual contention in SQL, because that's the shared resource, that's a bit of an issue. Because then any contention escalation in SQL then ripples to every single thing that's using it. If it's just a client-side, well, I might just live with it. We would also need a way to constrain concurrency client-side. Because in any world where new work shows up and I just spawn another thread to go do that work is unbounded concurrency. And unbounded concurrency in conditions of extreme success equals crashing. So your devs need to go, you cannot ever call, say, more than 10 of, you can't basically call that stored procedure more than 10 times concurrently. And if you get so much load that you basically start stacking up, throw the data away. This is a lossy system. It's okay to throw data away because it's better to throw the data away than either infinitely building up data, because it's logs. The most relevant operational data is the most recent operational data. It's very common in systems like this to enforce strict FIFO queuing, first in, first out. Working on a system a few years ago, it was built that way. They triggered basically a bug in the code that generated 100,000 log records per second per machine, with strict FIFO ordering that could deliver 100 messages per second per machine to the backing store. So you guys are smart. You're going through the math here, and you're thinking, how long did that take to catch up? We don't actually know, because after 3 weeks, we just reset the thing. Basically, you get these interesting live locks where all of the interesting relevant data gets stuffed up behind the irrelevant data. So unless you have the way to bleed pressure in the end-to-end flow, awesome, you guys rock, thank you. Well, I spoke too soon. There we go, there we go. Unless you have a way to bleed off the pressure, you basically, from the SQL Server side, everything's working fine and you're ingesting data, but it's not relevant data because it's so old. We haven't talked anything about query performance yet. I don't know how fast I can get data back out, and write-only systems are not very useful. They're easy to create, but they're not very useful. And kind of the bigger question is, Mark, where did all the exception logging go? Because I took it out at the very beginning when I couldn't fit all of the data that I needed into a single SQL page, and I never put it back in. This is a deliberately incomplete exploration. The answer for how we put exception logging back in is actually you have two table-valued parameters, one containing the applications, one containing the exceptions, and then you do two inserts. Yes. All right, so since we're nearing the end of our time together, quick recap on the destination. SQL Server can be a reasonable store for operational logs, especially if you don't have either an unknown or burst load system. You really do want to use memory optimized tables with batching to get a reasonable performance, but the higher order bit is batching, not the memory optimized tables, unless you have IO or transaction log issues. You absolutely have to push a certain set of choices and changes upstream to the application. You cannot solve all these problems in SQL, no matter how hard you try. Well, you may be able to. They're just so much more expensive to solve at just one tier. But ultimately, everything I've talked about for the last hour is not a good idea, depending on context. For doing truly high-scale systems with structured logging, SQL is actually not a great store, because you have to spend a lot of time building up all the appropriate stored procedures and tables. And that's where you want to put your most expensive, most valued data that's highly curated. This is log data. It's digital exhaust. You're going to end up throwing 90% of it away. For truly large-scale systems, you're actually probably better off using Elasticsearch, Logstash, and Kibana, commonly called the ELK stack, in order to provide essentially full text indexing over logs at bulk, and then using SQL to basically create operational data marts that pull together pre-processed structured data into a more explorable form. Again, not that SQL doesn't have a place, but in the really high-end systems, this is probably not the best choice because you start fighting against physics and you start fighting against economics. But the key thing is, if you have the decision process and the structure for measuring, evaluating, and also taking into account the economics, you can always kind of get to a good place. But more importantly, it's the journey. The journey is more important than any specific destination because how you got there and where you go from there is really the kind of key thing at the end of the day. And having a really rich data-driven engineering approach, thinking about end-to-end, thinking about repeatability, and being able to back all of your engineering choices with data is fantastic. And the averages tell lies, dirty, nasty lies. If we go back to a couple of those graphs, if you think about just right here, let's just see, yeah. You know, let's get a good example. Yeah, if we look at the average and the max, in this case it's actually throughput, so it's inverted. The average is pretty good. The max is dramatically different. So again, if I only ever look at the averages, I'll never know if there's these outliers hiding in here that can do bad things. So you can't trust your averages. Which also comes back to why high volume production logging is important. Because if we didn't have the ability to log and analyze every single call chain through that system, we never could have produced any of this data and had an understanding of what worked and what didn't. So this is actually a glimpse into a future patterns and practices project. Anyone familiar with patterns and practices? A couple hands. And it's basically a group at Microsoft that happens to work for me. And their job is essentially to take a lot of what we've learned about building high-end systems, high-end distributed systems with an eye towards Azure, and basically publish repeatable content on how to do this. We publish all of our stuff on GitHub, github.com/MSPNP. And in the next couple of months, essentially there's going to be a series coming out on high-scale operational diagnostics and logging. And you're getting kind of a little glimpse into the process we're going through to find out what works, what doesn't. But more importantly, not just say this is a proven practice, but here's why it works and in which context. And if you step outside, bad things will happen. All right. That's pretty much a little walkthrough, kind of a day in the life of CAT, some of the things we think about, some of the approaches we go through, and some of the areas we're exploring, specifically with regards to operational diagnostics, insight, and data-driven engineering. I'm happy to hang around for a little bit before the next speaker kicks me off, and if anyone's got any questions, because I think we are actually out of time. But other than that, thank you for letting me, oh, sure, a couple in the front here. Yeah.
You mentioned Elasticsearch. Would you recommend that you do your log insert directly into Elasticsearch?
So the question is around what I recommend doing log inserts directly into Elasticsearch. So for folks who aren't familiar with it, it's essentially a distributed data indexer based on top of Lucene. And you have a couple of options. You can either push data directly in, or you can have some form of intermediary buffer. There's pros and cons on both sides. One way says every machine just cranks open a socket to Elasticsearch and just hammers data. That actually works really well. But the other side is, if you think about that feed of data, it's actually really valuable. And if you have multiple consumers of the data, if you wanted one view in Elasticsearch, one view into HD Insight, and one view into, say, actually a partial view into SQL, then going through some form of intermediary buffer, essentially using Logstash to route data into, say, a RabbitMQ or Event Hubs in Azure is a better technique. Basically, how many consumers do you have, and how coupled do you want the producers of data with the consumers of data? The good news is, if you're doing it, say, from NLog, it's just changing the target, so you're not locked in. Yeah. One more, and then I'll have the closure.
Part of your suggestion that you can do like on average, you have this step in R where you use the apply. I have a like alternative solution there where you can have like box plot where you have more information and it takes only 2 lines of code in R, and you can have a summary. And do you think it would be more like intuitive to use box plot where you see in the graph median, IPRs and other stuff instead of having bar?
So this is where I go back to the I am a novice at R, and if you have cool techniques, I would love to hear them and love to show them.
So actually take 2 lines to have a like.
And if it's 2 lines, that's even more awesome. And again, a lot of it's just going to be who are you telling the story to? If you're telling the story to yourself, it's fantastic. If you're telling the story to others, and having different techniques and different visualizations is fantastic. And I go back to, I failed stats in university. All right, thanks, folks.